So let's look for a less specific microscopic model for quantum measurement. Let's look for a model where the Schrödinger equation is what's really going on, so we don't have to have two postulates and two different kinds of dynamics, but that the measurement postulate, this wave function collapse, is a kind of emergent phenomenon. It's what happens on average, just like we have a microscopic kinetic theory and then we have thermodynamics. Let's see if we can develop that. It turns out that this problem was tackled a long time ago by John von Neumann. Von Neumann did some of the best work in the 20th century on both mathematics and physics. He did original work in logic, set and measure theory, fundamental quantum mechanics, game theory. He virtually invented automata. He was a computer science pioneer. He was famous in the field of hydrodynamics. So the story goes that one day von Neumann was asked to solve the famous fly puzzle. This is a puzzle where you have your hands a meter apart and a fly is flying between them, one hand to the other, and it's flying at 10 meters a second. And you move your hands together at 1 meter per second, and you're trying to squish the fly in between them. And the question is, how far does the fly fly before you get your hands together? And of course, the easy way to do it is to say, I know how long it takes the hands to come together. I know how fast the fly is flying. The hard way to do it is to figure out how far it travels until it reaches the hand there, and then how far it reaches and so forth. And you get this infinite series, and you add them all up. And if you see people doing it that way, it's really hard, and they have trouble. So the legend is that von Neumann just looked, went, oh, and gave the answer. And they said, oh, you saw the trick. And he said, what do you mean? They said, well, some people try and solve the infinite series. And he says, yeah, that's what I did. He was also a key figure in the Manhattan Project, and he calculated the exact right distance above Hiroshima to explode the first bomb in order to maximize the number of kilo deaths. He also strongly advocated for a first strike upon Russia in the Cold War, which probably would have ended the world. So genius always has some limits. His description of a microscopic model for quantum measurement is one of the ideas that has really stood the test of time, however. He argued thusly, the observable that you get in a measurement must have something to do with the interaction between the system and the measurement device, and have something therefore to do with the measurement device. Let's figure out how it has to work in some limits. Supposing my system is in state A, and my measurement device has to start in some kind of state, so we'll call that state 0 for the measurement device. Okay, now if we interact these two, and if we assume that that interaction has to follow the Schrödinger equation, then this is a unitary evolution. Then if we interact those two, what are we going to get? Well, the measurement postulate tells us that we must still be in the state A. So in other words, if A is one of the possible results of our measurement, if we were 100% definitely in that state, then we should stay in that state. Now, what state is the measurement device going to be in? Well, obviously, the measurement device is going to be a very large system, typically. It's going to be classically big. It's going to have enormous numbers of degrees of freedom. But whatever it is, whatever that state of that measurement device is, it's going to have some kind of state which we could recognize as having measured the state A. So that may seem a bit of a cop-out. All I'm saying there is that there is some kind of state that the measurement device can be in that will recognize that it has measured A. So if it definitely had the value A, this observable, then we would measure that and the device would register that we'd measured that. But what if it was in state B? This is a different possible eigenstate of our observable. We're starting the same initial state for our system, but this time our evolution has to give us something else. So it's the same evolution because it's the same Schrödinger equation. However, this time we have to be in state B. And this time our measurement device has to be in some different state. It has to be in a state that thinks that we've measured B instead of a state that thinks we've measured A. So our microscopic model doesn't have a lot of details in it, but the kind of results we have there are basically incontrovertible. Our evolution, our Hamiltonian evolution, if that's going to actually give us our final result, has to perform in that way. It has to turn A with the initial state into A with the measurement device having measured A, and B has to turn into B with the measurement device having registered B. And now the punchline, of course. What if we start with this state? Well, when we apply our unitary, we know exactly what we're going to get because the unitary evolution is linear. And the key point about that, of course, is that wave function collapse hasn't occurred. There was no real hope that wave function collapse could ever come out of this because the linear evolution is linear. And measurement is clearly nonlinear, it's clearly probabilistic. The Schrödinger equation is deterministic, and the measurement is clearly probabilistic. All right, so we just didn't have any hope. What we were hoping to get is something like this. And we got that, but we also got some cross terms because we started off in a pure state. And so this coherence here, this factor of I, is going to turn up in the off-diagonal elements of our density matrix. The only way we actually get the diagonal density matrix if we then go ahead and trace over some extra system. Well, what happens if we entangle with some further system? Well, by exactly the same extension, if we start from here, so supposing I walk into the room and I don't know what state the system is in, so I'm going to come in ignorance, so state 0 for Joe. then if I also follow Schrodinger evolution, then it's pretty trivial to show that the final state of the system is going to be, which does of course assume that I am describable by quantum mechanics, that I am an element of a Hilbert space. But given that every single component part of me is described by quantum mechanics and is an element of a Hilbert space, it seems some hubris to assume that I'm somehow special, much as it pains me to admit it. Anyway, we now have enough information to clearly state what's known as the measurement problem. So standard quantum mechanics tells you that when you make a measurement, wave function collapse occurs, but it doesn't really tell you what a measurement really is. It doesn't define the term. If you don't know when wave function collapse occurs, you can't make accurate predictions. Wave function collapse changes the coherence of a system, and so its exact timing affects what you expect to see at the end. Now, when you're talking about very big coarse measurements, of course, you don't see any problems here because it happened somewhere in the chain and coherence went away. But if you talk about situations where you have lots of control over the quantum state of the system, which has really only been possible over the last few decades, then these kind of questions really matter. And finally, we've just shown that wave function collapse cannot be an emergent property of the Schrodinger equation, which means we really do have to have both postulates. We have to have Schrodinger evolution sometimes and wave function collapse to others, and we don't know when wave function collapse happens, and we need to. And that is a summary of the measurement problem.